we're going to finish talking about valence bond theory and hybridization. So what we've already done is really cover all the theory that we're going to cover, but behind how hybridization works and behind how valence bond theory works. But what we haven't covered is how do we actually solve problems doing this in a really quick way. So we're going to do that. This is going to be a more practical lesson in hybridization. And once we do that, we'll move on to now talking about energies and enthalpies of chemical reactions. So this is a real shift. We spent a while talking about single atoms, and then we've spent most of the material since exam 1 talking about bonding. So now we're taking it one step further, and we're going to actually get to talk about some chemical reactions. So we'll do that once we finish up with our hybridization unit here. All right, so how do we go about determining hybridization in complex molecules? It's actually incredibly simple, and all that you need to do is think about, for the given atom that you're looking at, what you want to do is add up the number of atoms that are bonded to your central atom, or the atom you're considering, and add to that the number of lone pairs. And what you end up with is the number of hybrid orbitals that you need. All right, so the theory behind hybridization and picturing everything, that can be pretty complicated, and I do want you to understand that. But if, for example, on an exam situation, you don't necessarily have to think through everything. You can just use this very quick way to figure out the number of hybrid orbitals that you need. And what we just said is that anytime we need 2 hybrid orbitals, we know that the hybridization of that atom is going to be sp, because it's made up of one s and one p orbital. So let's say we need 3 hybrid orbitals. What is the hybridization of our atom in this case? Yeah, it's sp2. We want to take 3 atomic orbitals to make 3 hybrid orbitals, so it's going to be sp2. So what if we need 4 hybrid orbitals? What's the hybridization going to be in this case? sp3. All right, great. So really, that's it. Hopefully, hybridization just got a lot simpler for any of you that have been struggling a little bit with it. But let's go ahead and do an example to make sure that we can all do this. And let's take a look. Oh, first, let me mention an exception here. The one exception to thinking about how many hybrid orbitals that you have are in the case where you have single bonded terminal atoms. So in the case of a terminal atom that is a single bond, you're not going to hybridize it. So in that case, just don't even change anything. It's just going to be one of the p orbitals, or unless you're talking about hydrogen, in which case it will be an s orbital that overlaps. All right, so we can illustrate this with an example of formyl chloride. So this is a good example because we're just dealing with our carbon as our central atom here, and we have 3 terminal atoms, 2 of which are single bonded, so we're not going to hybridize those, and one which is double bonded, the oxygen, so we will hybridize that one. So in terms of thinking about the carbon, what is the hybridization around the carbon atom? All right, I'm hearing some mixed answers, so let's think. So the carbon atom is bonded to 3 different atoms, and it has no lone pairs. So what's the hybridization? Good, sp2. So if we're talking about the CH bond, we're going to say that it's carbon. It's a sigma bond because it's a single bond, and then it's carbon 2 sp2 bonded to a hydrogen 1 s orbital. All right, so let's take a look at the carbon-chlorine bond here. Again, carbon is still 2 sp2. It's the same carbon atom, and it's going to be a sigma bond because it's a single bond. But what about the chlorine? What atomic orbital is going to be bonding in the chlorine? All right, I'm hearing a little bit of mixes. They're all P's, which is a good start. It turns out that it's going to be the chlorine 3PZ. So the reason that it's P is because we're not hybridizing it. And the reason that I specifically say that it's the PZ instead of the PX or the PY is remember that the Z axis, that's our bonding axis. That's our internuclear axis. So anytime we have a p orbital that's involved in a sigma bond, it has to be the Z orbital because that's the only one that has the right orientation to overlap along that Z axis. So we're going to say it's carbon 2 sp2 and then chlorine 3pz. All right, so let's look at the last bond here, which is a carbon-oxygen double bond. We know that anytime we have a double bond, it's made up of 1 sigma bond plus 1 pi bond. So when we look at the carbon again, that's 2 sp2 But what about the oxygen? What's the hybridization of this oxygen atom? sp2. So we're going to have carbon 2 sp2 plus, and then oxygen 2 sp2. It's sp2 because the oxygen is bonded to one atom plus 2 lone pairs, so we're going to have a total of 3 hybrid orbitals. All right, so this is not our only bond. We have a double bond, so we also need to talk about the pi bond. So if we talk about the pi bond, we can say that's carbon 2py, then the oxygen 2py. We could alternatively say and be correct that it was the carbon 2px and the oxygen 2px. Either one of those is fine. All right, so that's an example of how we can assign very quickly and very easily what the hybridization is of a given atom, and then also fully describe the symmetry and the atomic or hybrid orbitals that make up bonds. So this is a lot of your problems on the P-set, so if you haven't finished that section, hopefully you'll be able to get through that section pretty quickly when you go back to it.